let's say, of an RC circuit. Okay, so I will draw an RC circuit representation. This time we will include an inductor, a current source here. This will be our current source. Then we will be having a resistor here. Again, I have a switch here, and then I have a capacitor here. Oops. So this switch will be closed at t is equal to 0. And then this capacitor might be charged with an initial voltage of V0. And then we will be calculating the VC, the voltage across the terminals of this capacitor. And then what else? So we have this resistor, we have IS, this is the current of this current source. Let me see if I forgot anything. I think that's all okay. Then this capacitor is C farad, whatever that C is. Let me see. Okay. So now we have this representation. So what happens here is before we close the switch, the capacitor might be initially charged with a voltage of V0. And then we suddenly connect that current source to the circuit so that there will be a step change in the current of the circuit, which will also affect its voltage as well, of course. And then we will try to solve we will try to analyze for this for the capacitor voltage, and then we can of course also solve for the capacitor current. That will be very easy. So I will try to do the. So okay, that is a very nice question. Thank you. I think we should definitely. I will just write this with a different color. So your friend is saying why we said V0 and VO and VC same time. So this is the initial voltage. So the initial charge, and then this VC will be like this will be VC of t. Let's say just to separate. So V0 is the initial voltage on the capacitor, and VCT is the time-dependent voltage. It will give us the time-dependent change in the voltage. So we will calculate this VCT, and this is the initial value. So basically, V0 is VC0. Okay, so that is the difference. Okay, so when this switch is closed, suddenly, what is going to happen here? So we will have an IS pumped here that will be divided into two branches. One will be the resistor, one will be the capacitor. And then in this case, we should be solving for the capacitor voltage. So I can just write a KCL here just to start, and then we will see what happens. So the IS here will be equal to, so this one will also be VCT, right? They are parallel with the capacitor. So the current flowing through this branch will be VC divided by R. And then current flowing through this branch, which is the capacitor current, and its direction is in this direction. So that will be, I think, C times dVC over dt. Is this okay for everyone? And if you remember, this is so much similar to this equation, right? We solved for the inductor case, for the RL circuit. So now we have this equation, and again here we need to solve for VC. And again, this is a first order differential equation, but there's a force response. Since we have this constant here on the other side, we will just apply the same tricks and solve for this. I will try to do this faster than of course the inductor case, since we already did one of them, but let's see how this will go. So this is, let's say, dVC over dt. Please follow the calculations so that you can warn me when I make any mistake. So that is IS over VC divided by R, right? That is going to be, so that will be C times dVC, which is equal to this. And then I can divide everything by the C. So this will be dvc over dt is equal to 1 over c times is minus vc over r, right? And then I can again take that r out so that I can have rc here. So that rc, because I know that rc is the time constant of an rc circuit, so that will be very helpful for us. So what I'm going to do is, let me see what I can do. So I want to write this as 1 over maybe minus rc. So I want to write this as minus 1 over rc. So in this case, this will be vc minus, can you help me? So I think it will be minus is times r, maybe. Can you double check this? So I'm trying to convert this to this form so that I can have minus 1 over rc, which will be minus 1 over tau. That will be very similar to our previous solutions. Can you double check this? So I had this minus, I took r out, so that will be plus vc, I am sure. And then here I took an r out, so I need to multiply is with r, and then I need to make it minus. I think this is correct, but please go over this calculation, because I don't have the steps here. I only have the final result. I can't compare the step, but we can of course compare the final result. And then this is again so much similar to what we have done before. So this part depends on VC. I will take it to the left hand side, so that this will be dV over VC minus IS times R. So these are dVC, of course. And then this is going to be minus 1 over RC times dt. Okay, so in this case, now what I can do is I can take the integral of both sides, but I need to do the integration state variable change so that I can do the integration, utilize the integration constant. So this will be starting from the initial voltage to any final voltage I would like to calculate. So that will be dx over x minus is times r. And if you are following, this is really very similar steps with the one we did for the RL circuits. So that will be from 0 to t dy, and then now I can do the calculation here. So that is we know that is ln. So so this one is going to be ln of I can simply write this I will skip some steps, but you can follow the solution. This will be divided by VC0 minus IS times R, right? And then here, this is C minus 1 over RC times T. Please verify the calculations I make. And then now if I take exponentials of both sides, that VCT is going to be IS times R plus VC0 minus IS times R times e to the minus T over tau, where tau is RC. Okay, please let me check with the final calculation I did before, IS times R, V0 ISR. I think that one is correct. And then I know what is this initial value is. That initial value is, we know that one is V0. I will just write it as V0 just for simplification. Okay, so this is all. This is the capacitor voltage. We can also calculate the capacitor current. So that will be ICT is equal to C times dVC over dt, right? So so that will be C times derivative of this thing. So this is constant. Derivative of this will be 0. Okay, let's not draw on it, so because we will be needing that VCT as well. So this first term will be constant. This is constant, they will disappear. We will only take derivative for this side, right? So, and the derivative of that, so this will include, so this will be, this is the gain, like multiplying e to the minus t over tau. Oh no. Give me a second. no, this is not just a constant, that v0. This thing is multiplying this exponential, so we will use it as is, and then we will have minus 1 over tau here as a multiplicand, right? So this is tau now. And then, and I hope I can make some simplifications here for ICT. So this tau I can replace with RC. So that C will cancel this thing, that R will cancel this, right? If I'm not doing a mistake. No, this can't cancel this one. No, it can. Let's see, those S's will cancel. So this R will cancel this guy, and then I need to add V0 over R here. So the result is going to be something like, I have a minus, so I will change their order. So that will be IS minus V0 over R times e to the minus t over tau. And we need to validate this because, so this is after 0. Let's check. I think that is correct, but is there anyone who did the calculations? Is this okay? So I will be deleting this. So we found these two items here. This is the voltage, and then this is the current with the step response. So can we write I0 for V0 over R? What is I0? V0 or VC0, which one is? So this is, V0 is VC0. I mean, like this V0 is VC0. But we labeled it before, so I didn't care. Aaron, I really don't understand what you're saying, but I think you're okay. Yeah. Okay, so now we have the step response solutions for an RL circuit and RC circuit. They are quite simple. Let me see if there's a quick example we can make. Oh no, it will take a lot of time. Okay, that is very bad. Okay, then I think that will be a good time to stop for today because it will take more than 10 minutes. I don't want to spend your time, but let's just